So we're continuing on with our example problem, looking at an air conditioning application that has humidification as well as a heating section. So we have heating and humidification, and we have wet steam coming in. And what we did at the end of the last segment is we were able to get to the point where we were able to compute the mass flow rate of dry air. So what we're now going to go ahead and do is look at an air balance. So we have mass flow rate of air at 1 equals mass flow rate of air at 2 equals mass flow rate of air at 3. So we're not adding or removing air at any point, so that one's pretty simple. And then the one for the water balance, the place where we have water addition is between 2 and 3, so that's where the interesting things happen. What we can say first of all is mass water at 1 is equal to mass flow rate of water at 2. We're not adding or removing. And so with that, we can re-express this in terms of mass flow rate of dry air. And with that, we can say the specific humidity at 1 is equal to the specific humidity at 2. I'll put that in a red box because we may use that in a moment. Now for between 2 and 3, what's happening there, we're doing the wet steam injection. Actually, it's a saturated vapor that we said. Now I can express the first term in terms of the specific humidity. So omega 2 and then the mass flow rate of the dry air. Mass flow rate of water coming in, and that has to be equal to what is leaving the right-hand side of our duct. With that, I can isolate the equation for mass flow rate of water in. And we get that expression, and I will box that as well because we may come back to it. Okay, so looking at this equation, what we know thus far, we know the mass flow rate of dry air, and that's it. We have specific humidities here, so if we can start to determine what the specific humidities are, we can start solving some of these things. So let's take a look at specific humidity. And this goes back to the equations that we looked at in an earlier lecture. Now we determined the vapor pressure, it's right here, at 1, and that was for the moisture, the humidity in the air, the water vapor, and consequently what we can do is we can plug it into this equation here, and with that we determine first thing specific humidity at 1 is equal to that, and then at 2 it's going to be the same value because we're not changing the amount of moisture, water vapor in the air between 1 and 2. So that's good. Now let's take a look at the humidity at 0.3, or the water vapor specific humidity. Now we know there the dry bulb temperature we were told was 20 degrees C. So what we can do, we can go to the steam tables in the back of our book. And at 20 degrees C, the saturation pressure is 2.339. So that's from the steam tables. And with that, we can then go and calculate the partial pressure due to the water vapor. Once we have that, we can put it into the equation that enables us to calculate the specific humidity. And P here would be the 95 kPa, or atmospheric pressure. And then we get 00933 for the specific humidity at state 3. So there we have specific humidity at 1, 2, and 3. What can we do with that? Well, let's go back and look. If we look at this equation here, we can now calculate the mass flow rate of water coming in. So let's do that. And there, so what we've determined, that was what they asked us to determine for part C of the problem. So that is the mass flow rate of water coming in. Now the next thing that we will do in solving this problem, we've done our mass balance for dry air and water. The next thing we'll do in the next segment is apply the first law, and with that we'll be able to put together the other pieces of the puzzle.